This video is to help you get a little more practice and reinforcement on working out Charles' law, Boyle's law, and Avogadro's principle. I have slated to work out the odd problems, but I have thrown in one even problem. So let's go ahead and get started. Question number one. It says that a gas system has an initial pressure of 2,680 torr with a volume unknown. So again, we want to identify the variables. So as we see them as we go along, let's go ahead and note them. So we have an initial pressure, so initial pressure is a P1 with the volume unknown. When the pressure changes, so we have a P2 to 2,240 torr, the volume was found to be 6.62, so we have a V2. The question is, and there should be a period right there, the question is, what was the initial volume in milliliters? So we're looking for this, or we can just say that we're looking for this here, so the initial volume. So again, I made a note up here, that says to make sure that you answer the following questions. Be sure to show all work, show all units. Also, be sure to rearrange the variables before solving any of the problems. This is just a good practice to get into. I know a lot of you don't really like rearranging variables, but once we start working with more variables, this is going to be a good practice for you, a good skill set to have. So looking at this question here where we have an initial pressure, a final pressure, an initial volume, and a final volume. All right, so we have the different types of equations, and you have to be able to decide which expression it is that you wish to use to solve for this type of problem. So when looking at, say, the different scenarios, and again, these are the different types that you'll have for the quiz and for the test. You'll have Dalton's law, you'll have Charles' law, you'll have Boyle's law, and Avogadro's principle. Now, you don't really need to know the names of those, but you do have to recognize the variables. So like with Charles' law, we have a volume-temperature relationship. With Boyle's law, we have a pressure-volume relationship. And then with Avogadro, we have a volume and a number of moles relationship. And Dalton's law of partial pressures only deals with pressures, so there's nothing else involved there. And you have at least at least two or three different types of gases involved here. So looking back at the problem, we have a starting pressure, a final pressure. We have an initial volume that we're solving for, and a final volume. So the equation or the expression that we'll use is this one. It's a Boyle's law equation. So let's go ahead and write that down. So we know that we'll be using P1 V1 is equal to P2 V2. Now again, we're looking for, in this case, we're looking for V1. So since we're looking for V1, let's move or divide P1 on both sides. So now my equation looks like this, where I have V1 is equal to P2 V2 all over P1. And I'll admit, that is probably the hardest part of this whole problem, is rearranging the variables. First of all, deciding which expression to use, and secondly, making sure that you rearrange the variables. So let's go ahead and move this guy down here so we can actually have a little more room to work. So let's go ahead and plug in our variables. Now, before we go any further, we have torr that are listed here. The question doesn't say anything about changing the torr, and we really don't need to, because when we put the pressures over each other, those units go away. However, when we look at the volume, it wants it to be in milliliters. We can do that at any point. We can either change the volume now, or we can do it at the end. Some of you want to do it now, so let's go ahead and get it out of the way. So if you start with 6.62 liters, and you need to go to milliliters, you're going to move your liter down here, and your 10 to the 3 milliliters up on top. So that's going to give you 6,620 milliliters. And again, you can do that at either this point in the problem or at the end. Now with temperature, you must change the temperature at the beginning of the problem. You can't wait until the end to do it, because it'll mess up the math and everything. All right, so let's plug in our values. So my initial pressure, our P1 is 2680 torr. My final volume, which is what we changed to milliliters, is 6,620 milliliters. and it's all over the initial pressure, which, oh, I'm sorry, I have those pressures backward. So let's move that down here, okay? So that's one reason why I label. Make sure that you actually put the correct value with the correct variable. So P2 is actually the 2240 torr. Okay. So again, even though I was a little quick in writing the values down, that's one reason why you want to make sure that you label your values or your variables. It probably would have been a little better to maybe put the P2 down there. That way I'm not looking at those two values on accident. As I look at it more and more, it probably was bad to label the P2 like that. Just put it right there. Okay. So that one represents P2, that one represents P1. Okay. So once we have our values in place, again, the torrs cancel out. We have to have a like units to cancel out. So if that was in kilopascals, we would have to convert either that to kilopascals or that into torr. But they're in the same unit, so we're good. So let's find out what these values. And we get a value of around 5,533, so 5.53 times 10 to the 3, and that is in milliliters. So 5,533 milliliters, okay? All right, so let's look at question number 3 since we're doing the odds. Number 3 says a gas system has an initial volume and temperature. So an initial volume, so here's our V1, and an initial temperature, T1, of 8,330 milliliters, 335.3 Kelvin. It's already in Kelvin, so we're good. If the volume changes, so that's my V2, what will the resultant temperature be in degrees Celsius? So it wants you to give the temperature in degrees Celsius. However, we cannot change that degrees Celsius until the end. We have to use Kelvin within the math, or else bad things could happen. All right, so let's go ahead and plug or decide which equation are we going to use. So again, we have a volume and a temperature relationship. Actually, what will the, I'm going to find out what that is. So we're looking for our final temperature, and we know the volume. So we're looking with Charles' law, or the V1-T1 relationship, except we want to make sure that we use the correct equation. And you'll notice that for Charles and for Avogadro, I have an or here because we want to make sure that the variable we're looking for is on top. So the value or the variable that we're looking for is T2. So we want to use the equation that actually has T2 on top or in the numerator. So we're going to use that equation there. So we'll have T1 over V1 is equal to T2 over V2. All right. And since we're looking for T2, what that means is we're going to multiply V2 on both sides. So my equation now looks like T1 V2 over V1 is equal to T2. All right, so everything's good. The milliliters or the volume units are the same, so we don't have to change anything. The temperature is in Kelvin, so we're good. We'll change the degrees Celsius at the end. We have to wait until the end. So let's go ahead and plug these in. So T1 is 335.3 Kelvin. And V2, so 5080. And then my initial volume was 8,330. And the units that cancel out are milliliters, so we're left with Kelvin. So let's find out what that is. So that gives me around 205. Now my calculator says 204.481, but again, 3 sig figs is nice. Okay, so 205. All right, looks like we have some bonus footage here. Number 4, it says a sample containing 3 gases are within a 10-liter container at the same temperature. Calculate the partial pressure of each gas. If the total pressure within the container has a pressure of 476 kilopascals, within the container, within the container there are 45.3 grams of nitrogen gas, 187.1 87 grams of argon gas and 34.1 grams of chlorine gas. All right, so there are a lot of things going on here. However, the equation that we're going to use is that one, because we're looking for the partial pressure for each gas. So what we want to write down or take note of is that the total pressure, PT, is equal to that. So our total pressure, which is equal to 476 kilopascals, is equal to the partial pressure of, looks like, nitrogen gas, of argon gas, and argon ends in ON, not gen or ein, so it's just AR, and chlorine gas. So chlorine ends in the INE, so Cl2. Okay, so that's what our equation looks like. So we have our total pressure, we have the parts for each. However, we're given masses. So whenever you're given grams or mass, make sure you change those to moles. So let's do that first. So we have 45.3 grams of nitrogen. We want to change that into moles. So 1 mole of nitrogen is 2 times 14.01. And we'll get a value for that here in a moment. We have 187 grams of argon. And 1 mole of argon. Now let's look at our periodic table. And argon is a noble gas, and it has a molar mass of 39.95. So 39.95, and we don't multiply that because argon is not diatomic, and we'll find out what that is here in a moment. And the last gas is 34.1 grams of chlorine. 34.1 grams of chlorine. Since it is diatomic, we have 2 of those. And that's 2 times 35.45. All right, so let's find out how many moles of each we have. This is nitrogen's 1.6, we'll say 2, and 4.68. This is 0.4481, we'll say. Okay. So there's our moles of our gas. So let's add all of those up. So we're going to add all these numbers of moles together, and that equals 6.78 moles. Okay. So what this is saying is, I have my moles of nitrogen, I have my moles of argon, I have my moles of chlorine, but this is my moles of gas. Okay? So once I have that, now if I'm going to find the partial pressure for each gas, I have to determine how many moles each of these gas makes up for the whole. So I've already calculated that, so let's do that. So let's see here. To find the partial pressure due to nitrogen, so nitrogen, I want to look at this. 1.62 moles of nitrogen makes up the 6.78 moles of gas. I'm going to multiply that value by the total pressure, which is 476 kilopascals. Get an answer, whatever that is. And then we'll do the same thing with the argon. So the partial pressure of argon, again, we want to look at, we have 4.68 moles of argon, again, over 6.78 moles of total gas, and I'll multiply that times 476 kilopascals, get a number. And then the last one is the chlorine, which is 0.481 moles. So 0.481 moles over the 6.78. And we'll multiply that times the 476 kPa. And let's get some values. So that equals 113.5. I'll go ahead and put the 0.5 on there. This one equals 328.7. And this one equals 33 we'll say 8 kilopascals. And if I add all those up, I'll be willing to bet that that's equal to 476 kPa. Now, let's talk real briefly about why I did this, the mole fraction. Again, when looking at gases, the neat thing about gases is under the same temperature, under the same conditions, if I have 1 mole of each gas, they're going to behave in the same way by having the same number of particles and the same volume. However, we have different numbers of moles of particles. We have different gas particles, period. So to get an equalizer, we want to change those grams into moles. So we have to change them into moles, because if you look at this and you say, oh, well, I've got 45.3 moles of nitrogen and I have 34.1 grams of chlorine, those should be relatively close, except if you look at the chlorine's about 1/4 of the total nitrogen. Why is that? Because the masses are so different. In other words, chlorine weighs almost 4 times more than the nitrogen. Okay, well, not quite, but it's heavier. So that's one reason why we must change the grams in the moles. Once you have your moles, add up all the moles, and we're going to put them in the same container, and all those gases will contribute to a total pressure of 476. I want to find out what each of those gases is contributing. So I want to find out, okay, for nitrogen, of the 6.78 moles of gas, nitrogen is contributing 1.62 moles of that. So I'm going to take that divided by that. That'll give me my mole fraction, or actually my percentage, whatever you want to call it. So my percent of the total pressure. Then I do the same thing for the argon and for the chlorine. And as a real quick check, just add those up. If that equals or is very, very close, because again, depending on how you round, it should be very, very close to the total pressure. Number 5, a gas system has an initial pressure and volume, so an initial pressure and an initial volume of 58.7 kilopascals and 2,070 milliliters. If the volume changes, so V2, to 2.23 liters, what will the resultant pressure be in torr? Nice. So it wants to know what is the final pressure, and we'll change it into torr. Now again, nice thing about pressure is that we can change the units into torr now or later. However, temperature, you must change the temperature when you're given degrees Celsius. Here, temperature is not an issue. All right, so we have an initial pressure, we have an initial volume, we have a final pressure and a final volume. At this equations, we're going to use Boyle's equation or expression. Okay, so let's go ahead and write that in real quickly. So we'll have P1, V1 is equal to P2, V2. And since we're looking for P2, since I'm looking for P2, that means V2 needs to be divided on both sides. So my equation now looks like P1, V1 divided by V2 is equal to P2. Now, I'm going to move that down here so we can use that here in a second. Couple problems so far. I have liters and I have milliliters. We need to change one to the other. It doesn't matter which one you change. I'm going to change the milliliters to liters, but if you want to change the liters to milliliters, that is fine. You're still going to get the same answer as long as you do it correctly. So I'm going to change this. So I have my 2,070 milliliters. Change that to liters, and there's 1,000 milliliters in every liter. So that gives me 2.7 liters. I'm going to go ahead and change the pressure right now. Actually, let's move that up. Actually, let's move it up. Move it over somewhere. Okay. I'm going to change the pressure right now from kilopascals to torr. And if you don't want to do that and you want to save it till the end, that's fine. You can do that. So let's see here. So we have 58.70 kilopascals. Okay. Change the kilopascals into, I can't remember if I gave you a torr conversion. Remember that 1 millimeter of mercury is equal to 1 torr, so I'm going to go ahead and say that I did. So 1 kPa is equal to 7.501 torr. Now if you need to go from kilopascals to millimeters of mercury and then to torr, that's fine. No problem there. So let's find out what that is. 140. So the pressure is 440, we'll say 40 torr. Okay. All right, so now let's go ahead and plug these into our expression. So our initial pressure, which is the 440 torr, and the initial volume is the 2.07. That's liters. And my final volume was 2.23. Oh, 23, sorry. And what units cancel? The liters go away. We're left with torr, which the question is asking for, which is nice. And that's giving me 400 and we'll say 9. 409 torr. Okay. So again, I don't think this was too difficult of a problem. This is one that you should be very comfortable with working out. Again, make sure that you do your conversions. You have to convert one or the other, whether milliliters to liters or liters to milliliters, your call. They will cancel out, just like what the liters did here. So if you left it as milliliters, those units would cancel out as well. 7. A gas system has an initial volume, V1, of 4.15 liters, with the number of moles unknown. When the volume changes, so V2, under conditions of constant pressure and temperature, the number of moles is found to be, so our final number of moles, so our final number of moles in 2 is 0.222 moles. What was the initial number of moles? So question mark N1. All right, so we have a volume and number of mole relationship. So again, which equation? We'll use Avogadro's principle, but are we looking for moles or are we looking for volume? And again, if you're not sure, there it is, you wrote it down. So we're going to use this equation here. So we'll use the N1 over V1 is equal to the N2 over V2. And since we're looking for N1, we're going to take V1 and multiply it on both sides. So my equation now looks like this, where N1 is equal to N2 times V1 over V2. Okay? So again, rearranging the variables. So let's move that baby right down there. Is there anything that we need to change? Yes. We have liters and we have milliliters. So which one do you want to change? I'm going to change the milliliters to liters. It's easier to do that. So 4790 milliliters. Divide that by 1,000. So that gives me 4.79 liters. And I don't think we need to change anybody else. The moles are good. So let's go ahead and plug away. So the number of moles at the end was 0.222. Now we have to be careful here because this is our initial volume. So our initial volume is 4.15. So don't write the wrong one down. And then our final volume was the one that we changed. So 4.79, 0.19, we'll say 2. All right, number 9, the last question. A sample containing 2 gases are within a 6.5 liter container at the same temperature. Calculate the partial pressure of each gas. If the total pressure within the container has a pressure of 3.44 atmospheres, within the container there is 42.3% oxygen gas and 57.7% helium gas. Now, this question is a good one. And a lot of you initially are going to look at this question and ask yourself, what are you going to do? Well, be sure that you slow down. There's a lot of information in this question, but ask yourself, what is the question asking? And what is the question giving us that's going to help us answer the question? So the first thing you should do is, after you've read it at least one time, is ask yourself, what is the question? The question is right here. Calculate the partial pressure of each gas. Okay? That is the question that's being asked. What information is given to you that's important? Well, we know that the total pressure of the container is 3.44. Okay? The total pressure is 3.44. That is really important. So we know that we have this situation here where we have a total pressure. Okay? It also says that within the container there are two gases, 42.3% oxygen and 57.7% helium. Now, at the beginning of the question, it was information. It just said a sample containing two gases are within a 6.5 liter container at the same temperature. Is that information even important? Well, the two gases just is supported here because it gave us our percentages of that. But the 6.5 liters, you're not going to do anything with that. So this is what we call a distractor. So that is there to get you to stop and try to figure out how you're going to use the 6.5 liters. You're not. You're going to use your total pressure and you're going to use your percentages. So the total pressure is 3.44 atmospheres. We want to find out what is the partial pressure due to oxygen, and we want to find out what the partial pressure due to helium is, which will equal the total pressure. This question becomes a lot easier when you ask yourself questions about a question, because we know the total pressure and we know the percentages for each of these gases. So what are you going to do? That's right. You're going to take the percent and change it to a decimal. So what I'm going to do is show you that. Actually, let's leave that up there. So the partial pressure due to oxygen is 42.3%. I'm going to change that to a decimal. So I'm going to go 0.423. In other words, I divided it by 100. And I will multiply that times the total pressure, which is 3.44 atmospheres. I will do the same thing with the helium. Now remember, helium doesn't end in gen or ine, so it's all by itself. And in this case, it's 57.7%. So change that to a decimal. 57.7 multiplied times the total pressure. And then solve. So I get a value of 1.45, actually 46 atmospheres there, and 1.98 atmospheres here. Add those two together, I'll bet you get 3.44. Okay? So again, don't psych yourself out by looking at this question and saying, what are you going to do with the 6.5 liters? Absolutely nothing.